Hi, and welcome back to another lecture. Today we are covering section 10.1, which will be our introduction to radicals and radical functions. Now, before we can really jump in and have a conversation about radicals, we really need to understand a little bit about their structure. On the top of your notes, you do have this same information, but I'm going to go over it anyways, just because it's good for discussion. Now, as you can see with this problem, I have the nth root of A. And as I'm looking at this problem, the n value, which is sometimes invisible, and we'll talk about why in a moment, the n value is what we call the root or the root index. The a value, under the little squiggly looking bar there, that a value is what we call the radicand. Now, as we're looking at these two, you can convert from a radical value into an exponential value. So you have the nth root of A is equal to some value of B, whatever it solves out to. And this is the radical form. And it can convert back and forth between the solution, which is A, will equal to the B to the nth power. And this is going to be what we call the exponential form. So we worked with exponents a little while ago. Exponential form. There we go. We worked with exponents a little while ago. And so this is really just an extension of that discussion. But radicals do have some special properties, and that's why we're keeping it as a separate section. So with that in mind, let's go over some very easy introductory problems for us. Let's assume that I have the square root of 100. Square root of 100, some of you are probably already like 10. That's what it is. Let's talk about why. So what I'm looking at here is this root index is invisible. Ooh, that's awesome. Technically, whenever you have just the square root, we are talking about a root index of 2. So you can kind of think of it as there's a little 2 out there, but we just don't write it. Kind of like whenever you see a value like x, there's technically a 1 out here, but we just don't write it. So, same idea. There's a 2 here, we just don't write it, and that is our square root value. Now, to find a square root, we are looking for something times itself to be able to have two items, two identical items, or two identical terms. So this would be 10 times 10. Because I'm looking for a root index of 2, I need a pair of identical numbers to pull out, and thus this comes out to 10. Now, based on what we just said in our other discussion, if I were to look at it from this perspective, this is the radical form, right? Going from square root of 100 equaling 10. The exponential form would say that I have 10 squared is equal to 100, and that does work out. So my radical form and my exponential form are conversing back and forth. Now, this is just to give you an idea of proof. I am going to purely work through our radical forms for the remaining problems. Let's say I have the third root of 8, the cubic root or the third root of 8. I'm looking for something times itself 3 times to be able to pull that term out. So the cubic root of 8 could be broken down to 2 times 2 times 2. There are 3 2's here, so there are 3 terms exactly the same, and I can pull that value of 2 out of the problem. So the cubic root of 8 is 2. Let's get into another problem. Let's say I have the cubic root of 64. These will probably start going a little bit quicker as you get more practice. The cubic root of 64 could be broken down. So I have 4 times 4 times 4. There are 3 of the same exact term here, so I can pull that 4 out. And there's my solution. How about the cubic root of 125? Well, 125 could be broken down into 5 times 5 times 5. 3 of a kind, I can pull it out. And so I just have 5. And so you'll notice with these cubic roots that they're pretty easily identifiable. But let's say I'm looking at something like a fourth root of 16. A lot of people may not know their fourth roots right offhand. So how do you figure it out? Well, for this problem, it's fairly easy. But I'm going to show you the process anyway. You could technically break down 16 into 2 times 8. And this 8 can be broken down even further into 2 times 4. That's a 2. There we are. It's smudgy. There we go. And this 4 could even be broken down into 2 times 2. So what I'm doing is I'm actually breaking down my values into multiple pairs. And as I get to the set value of multiple pairs that I need, that are identical, I can then pull out terms. So here, I have 4 of 2 times 2 times 2 times 2. So that means I can pull out a 2 for the fourth root of 16. If I'm looking at the fifth root of 32, same exact idea. Split it up. So you know the fifth root of 32 can be 2 times 16. 16 can be broken up, so on and so forth. You know this one already because we just did it. So it's 2 times 2 times 2 times 2. So I have 5 2's here. 5 of a kind, I can pull out my 2. I don't know why I just wrote a 5. I'm so sorry. 5 of a kind, I can pull out my 2. Talking and working at the same time. Okay. Let's talk about the cubic root of 8/27. Ooh, fraction. Right? Fractions are actually not too bad. It's the same exact thing. So you have the cubic root. You're looking for something times itself 3 times. We already know 8 because we just did it. So that's like 2 times a 2 times a 2. What about the 27? How about 3? 3 times 3 times 3. So I have 2/3, 2/3, and 2/3. So I can pull out a 2/3 or a 2/3 because I have 3 of a kind for each. What about the square root of 0.0025? Ugh, decimals. It's terrible, right? Decimals are actually not too bad. Here's the thing. With a decimal, you have to understand that when you multiply a decimal by another decimal, you increase the number of decimals by however many you originally had. So in this case, I see 4 decimal places. I know my end result will have to have 2 decimal places because something identical times itself, I have 2 decimal places, 2 decimal places, in total I have 4. So in this case, the square root of 0.0025 could be 0.05 times 0.05. In total, I have 4 decimal places, and 25 broke up into my 5's there. So that means I have 0.05 as my end result. Again, root index of 2. I have 2 of a kind, and I pulled it out. Okay, so as we're looking at our root values, whenever you're solving so far in these examples, what we're solving are principal roots, meaning we're talking about the positive value of roots. Getting my board space back really quick. And so we assume that just the square root is a principal root. That's what we assume. Now, if you include a negative, then technically you're talking about a negative square root. So for example, the square root of 100, we're talking about the principal root here. The square root of 100 is technically 10, right? But if we were to say a negative square root of 100, this negative is completely separate from the square root. So you take the square root here, it's like you have negative 1 times that 10, right? Square root of 100 is 10. We just said that here. This negative is separate. Your end result here would be a negative 10. What about the fourth root of 81? That's our principal root. That comes out to 3 if you were to break it down. So it's 3 times 3 times 3 times 3. If I had a negative fourth root of 81, guess what? It's negative 3. So that's what I'm looking at. How is that different than the fourth root of a negative 81? Ooh, here's an interesting case. Let's take a look at it. This negative inside of the radical, if I were to try to apply it to everything, would be negative 1 times 3 times 3 times 3 times 3. Now here's the thing. If each one of these were negative, because I'm going to make a case in just a moment showing you where these would be negative, if these were all negative, that would be negative times negative is positive. Times negative is negative. Times negative is positive. This alone, without that negative 1, would become positive if these were all negative. But the problem is that doesn't give me a negative 81. So that's why I have this negative 1 out here separately. So what do I actually get? Something that I can't take the square root of. It doesn't work. It's not possible. So looking at the principal root and the negative square root, how is that different than if I had the fourth root of a negative 81? Because I see negatives here, but it's actually vastly different. So let's check it out. So the fourth root of negative 81, that would be like a negative 3 times a negative 3. That's positive 9, right? Times a negative 3, that's a negative 27 now, times 3. Well, wait a minute. Why isn't it a negative 3, right? Well, this is a negative result. So negative times negative is positive. Times negative made it negative again. If I would have multiplied by another negative, that's making it positive. And that doesn't work. So do I have 4 of a kind here? No. No, I don't. There's another little problem here. And this is going to be true of any even root index. Any even root index, be it 2, 4, 6, a billion, doesn't matter. What you're seeing is that your even root index cannot include a negative inside of the radical. Okay, so that means this does not exist. It is DNE, does not exist. So anytime you see a even root index with a negative inside of the radical, so the radicand is negative, this does not exist. It doesn't break down correctly. Now let's try an odd root index. I just want to show a distinction. So cubic root of 8 we said was 2 earlier. If I had the negative cubic root of 8, this negative is separate, so it's like a negative 2, right? But what if it's a cubic root of negative 8? Cubic root of negative 8. Well, let's see how that breaks down. That would be like a negative 2 times a negative 2 times a negative 2. So negative and negative is positive, times negative makes it negative again. So that works, cool. And all those 2's actually do work out to 8, so that's awesome. So this comes out to a negative 2. Huh. So, big note for you. Odd root indexes, or odd root indices, can have a negative radicand. They can have a negative radicand with a negative root index. Unlike an even root index, the even root index cannot have a negative radicand. So very big distinction. Please make that as a big note, flag it, and see what you see, or make sure you can see it on your notes for later. Okay, I'm going to jump into the next one. And I'm also going to introduce a principle that's not actually introduced just yet, but it will help you as you go. So I'm going to erase all this, get my board space back. Let's talk about the square root of x to the 6th. The square root of x to the 6th technically could break down so that you have the square root of x times x times x times x times x times x is 2, 4, and 6. There we go. Now that's fully expanded. This is a little overkill, but it's fully expanded. Now, looking at this, I'm looking for pairs. So I have a pair of x's here, I have a pair of x's here, and I have a pair of x's there. So I have x times x times x, which is x cubed. Now, if we were to look at this same concept, same exact problem, and split it up as x cubed times x cubed, isn't that a pair? Yeah. So did I have to fully expand it? No. That's pretty awesome. Now, you want to see something else really cool? Again, this is that principle that's not yet really introduced, but we'll work a lot with it later. But you can start using it now to get some practice. This is called power over root. So I have a power and I have a root. So I have a power on my radicand, my base here, and I have a root index. My root index is 2, right? My power here is 6. So the way power over root works, I'm going to get that erased really quick. The way power over root works is that I have a, my radicand, which is also my base, is going to be raised to a fractional exponent, and that is the power divided by the root. Now you only want to use this right now if you have a very equal breakdown, and this is what I mean. So I had the square root of x to the 6th. I have x, that's my base, to the 6th divided by, my root index here was 2. So 6 divided 2 is a whole number. That's very nice. You can do that already. That gives you x to the 3rd. Now notice, this is the same no matter how you do it. So if you fully expand, that's perfectly fine. If you just break it down so that you can see your pairs, that's fine too. If you want to start getting some practice with a concept that will be coming up later, you can also do that now. That is the power over root concept. It's also a rational expression is what they would say. Now, that being said, I'm going to do the next problem, but I'm not going to fully expand it. I'm going to show this method and this method. So the next problem that I have is the square root of x to the 8th. Square root of x to the 8th, I can split that up as x to the 4th times x to the 4th. So that is a pair. I have a root index of 2. That means my end result is x to the 4th. I could also say that the square root of x to the 8th is x to the 8th divided by 2 power, because I have power over root. So 8 divided by 2, which is x to the 4th. Same thing either way. It's a very good concept to learn, and practice is the power over root. Let's try another problem. Let's say I have 25x to the 14th as my radicand. So I'm taking the square root here. Square root of 25 is 5. And then I have x, 14. Who wants to break that down? Why don't I say 14 divided by 2? I could do that. What's 14 divided by 2? 7. So I have 5 to the 5x to the 7th. Let's try another one. This is the cubic root of negative 8x to the 12th. Cool. Cubic root of 8, that is an odd root index, so I can't have a negative here. Remember that. Cubic root of 8 is going to be 2, so that's a negative 2. X to the 12th, and I'm looking at a root index of 3. Well, that would be 12 divided by 3, wouldn't it? Power over root. So that would be a negative 2x to the 4th. Awesome. So let's get some board space here. Let's take a look at another problem. Let's look at the 6th root of 7 to the 6th. Now, notice with this particular problem, I have an even root index, and I have the same power on my radicand base. So what I'm looking at here, if I were to expand this, is the 6th root of 7 times 7 times 7 times 7 times 7 times 7. Make sure I got 6 of them, 2, 4, and 6, yep. I am looking for 6 of a kind. That is my root index, 6, so I'm looking for 6 of a kind, and I do have it. So my end result here is 7. Now, there's a rule here that's very, very important to know, extremely helpful for you, and that is if I have an even root index, so n, the nth root of a to the n is even here, my answer will be the radicand base, but the positive value. So I'm looking at the absolute value of a, and this is if n is even. Now, if n is odd, it's just the a value. So let's put this into practice. Let's say I have the cubic root of 20 cubed. So the cubic root of 20 cubed, I'm looking at an n value that is odd. So my end result here should be just a, that base radicand. So that would just be 20. Cool. Let's say I have the cubic root of negative 19 cubed. Notice how my negative 19 is the entire base to that exponent of 3. You can see that because it is bound here with parentheses. So I'm looking at an odd root index, the 3 here. It's the same exact value there, so that's nice. And that makes this a negative 19. What if I were to have the 6th root of negative 20 to the 6th? The 6th root of negative 20 to the 6th. Well, in this case, I'm dealing with an even root index, so this first rule. And I'm seeing that I have a negative 20 as my entire base, but I want the absolute value of that. So this means my end result is 20. Excellent. Let's try another one. I got plenty of room, so I'm just going to work them right here. So let's do the 5th root of negative 2 to the 5th. My base value is negative 2. I am dealing with an odd root index. And so I can say that my end result here is -2. It's beautiful because you don't have to fully expand these every time. We did in the first example, but with these two rules, identifying that your root index and your power are the same, then you can just jump to it, whether it's even or odd, and create your value based off your radicand base. Last one for this little section, we got the fourth root of -72 to the fourth power. So I'm dealing with an even root index here. And my base value is -72, but I'm wanting the positive of that. I have just 72. Okay. Now, radicals are pretty easy to work with. They do take a little bit of time, a little bit of practice getting used to, but they're very, very easy to work with. That being said, let's shift gears just a little bit by jumping into radical functions. Radical functions. So for example, let's say I have f of x is equal to the square root of x. This is the base radical function. It's as simple as it gets. If I were to look at this particular problem, the question that I would have first is, what is x? Or rather, what can it be? And what can it not be? So here's the idea. What if x is 0? What is the square root of 0? 0. What is the square root of 1? 1. How about the square root of 4? 2, so on and so forth, right? What if I put a negative value in there for x? I'm dealing with an even root index, so can I have a negative value? No, it didn't work, right? So here's what we're going to do. Let's solve for the domain, but we're going to make it very precise how we're solving for the domain. So we're going to say that x must be greater than or equal to 0. So it's slightly different in the way that we've been solving. We're saying that x is greater than or equal to, that's the different part, than 0. Because if I plug 0 in, that still works. If I have anything greater than that, that still works. If I have anything less than 0, I can't take a square root of a negative, so it doesn't work. So this is the base idea of our domain, which means our domain here would go from 0, including 0, so square bracket here, to infinity. That is our base function right there. Let's take a look at another example. Let's say our function is the square root of x minus 2. This minus 2 is outside of that square root. So be very, very careful as you read this. This is the square root of x minus 2. If I were to ask you what is the domain, you would say x should be set so that the radicand value is x greater than or equal to 0. There's nothing else to work with here, so that is my domain. It is from 0 to infinity. Pretty easy, right? Let's try another one. Let's say my function is the square root of x plus 6. Notice this plus 6 is part of the radicand. So the x plus 6, that 6 value, is part of the radicand. What I would do, I'm going to put a little dividing line here just to show some separation. What I would do is I would set my radicand so that it is greater than or equal to 0. Same exact process. But now I have a little bit of work. So let's try something. Let's go ahead and solve this out. So I subtract 6. I know x must be greater than or equal to -6. Ooh, a negative value. Interesting. So if I plug -6 into this problem, does it work? Well, what's -6 plus 6? 0. Square root of 0 is 0. You can do that. What if I plug -5 in? -5 plus 6 is 1. Square root of 1 is 1. That works. What if I were to put in a negative value such as -10? Negative 10 plus 6? Oh, that's negative 4. That does not work. And that is because you said that your domain is x, any value of x, must be greater than or equal to that negative 6. So this is your domain. You have to be very, very careful with these. Make sure you put it in the right format for interval notation. You have negative 6 including that value, so you have a bracket there. And it goes to infinity because it can be greater than or equal to. Let's try another one and just see what we get. Let's say we have a function where it is the square root of 6 minus x. So the whole radicand is 6 minus x. We're going to take that and put it so that it is greater than or equal to 0. Solve this out. I'm just going to add my x over. This is 6 must be greater than or equal to x. Remember, you're reading from the variable, so x is on that lesser side. You can also, if you need to, flip it. So I'm acting like this is a mirror. You could say x is less than or equal to 6 if you need to see it that way. Either way, you're reading from the variable. The domain here will go from negative infinity up to 6 and stop. Ooh, how do I know? Why am I including negatives? What's going on, right? Well, check this out. X is on that lesser side. And we just showed that here as well. X is on that lesser side. So if I were to put in, let's say, 0. 6 minus 0 is 6. I can take a square root of that. Let's say I put in, 10, positive 10. 6 minus 10 is a negative 4. That does not work. And that's because it is on the greater side of x. And we don't want that. We need x on the lesser side. So what if I were to put in, say, a negative, I don't know, pick a number, negative 50. Negative 50. Way out in the negative realm, right? 6 minus a negative 50. That's 6 plus 50, which is 56. Square root of 56, I can do that. It might be a decimal value, but I can do that. So you have to be very, very clear with your domain in terms of how you get it structured with radical functions. Now, that being said, I'm going to get some board space here, and I'm going to show you how this works for graphing. The first thing that you want to do with graphing is find out what your domain is. There's a very important reason for that, because you're going to be able to find out very quickly what your starting or ending point might be. So I have my function. It's the square root of x minus 2. I'm going to set my radicand so that it is greater than or equal to 0. Solving this, I know x is greater than or equal to 2, which means my domain is from 2 to infinity. Now, I got my domain first. Here's why. If you're graphing, you need an xy chart, right? It's also the same as an x and then f of x. But xy chart, you're graphing. I'm going to use 2 as my starting value. Here's why. I know 2 is part of my domain. In fact, it is the lowest part of my domain. If I plug 2 into this problem, 2 minus 2 is 0. The square root of 0 is 0. I've got my first point. Very easy. Very little work that I had to do. Now I'm going to pick another number. I'm going to say 3. So the function at 3 will be the square root of 3 minus 2, which is the square root of 1, which is 1. Awesome. Now, my next value, because we're not dealing with lines, we need multiple points. My next value that I'm going to work with here, I want to be a perfect square root. So I'm thinking to myself, how can I get a perfect square root here? If I just pick 4, for example, 4 is going to give me a square root value, which is also a decimal value once you calculate it out. And it's like, that doesn't work. But what if I put 6 into this problem? You might be thinking, how in the world did you get 6? Check this out. If I put 6 into my problem, f of 6 is going to be the square root of 6 minus 2. What is 6 minus 2? 4. So the square root of 4 is 2. Hey, look at that. It came out perfect. So what I'm actually looking at and how I'm getting my value is I'm thinking of what my end result should be in y. And then I'm thinking back to my value of x that I want. So I'm looking at my problem and I have x minus 2. I knew if I were to look at this, I want a perfect square root. So the perfect square root of that would give me 2 is 4. How do I get 4 out of this? I would have to have a 6 here. And so I'm mentally processing it that way and getting my end result. If you don't see it right away, and that's a-okay, don't worry about it, you can still keep getting values here, but as you're getting values, you just want to make sure you get to the point where you have whole number values, easy values to work with. All right, that being said, let's graph. So at 2, 0, I have a point. At 3, 1, I have a point. At 6, 2, I have a point. So that's 3, 4, 5, 6, and 2. There's my point. Now you might be looking at this and saying, hey, wait a minute, my curve, my line kind of bends a little bit. And you're absolutely right. Radical functions curve. So unlike a line which is straight, radical functions will curve. As your x values increase, your y values increase slowly. That's what's happening. All right, let's try another one where we are graphing, just because this is very good practice to get into. Let's say I have my function is the square root of x plus 2. The plus 2 is separate. First things first, get your domain. Set your radicand so that it is greater than or equal to 0. I know that my domain here is going to be from 0 to infinity. So if I'm graphing, guess what my first point is? It's going to be 0. I know if I plug 0 in here, square root of 0 is 0. Plus 2, I get 2. Now, let's try another function, or another input. Let's try an input of 1. Why 1? Well, the square root of 1 is 1. So square root of 1 plus 2 is 1 plus 2, which is 3. How about my next value? What do you think it should be? How about 4? The function at 4 is equal to the square root of 4 plus 2. Square root of 4 is 2, so that's 2 plus 2, which is 4. Just for giggles, what would be my next functional value that I would want to use? How about 9? If I plug 9 into this problem, that would be the square root of 9 plus 2 is technically 3 plus 2, which is 5. Notice how my x values are increasing by a lot, but my y values are very slowly increasing throughout this process. And so what you're seeing, you would need a minimum of 3 points. I've got 4. The last time I had 3. But what you're seeing is that you're getting that curvature as you continue to move down the x-axis. So at 0, 2, I have a point. At 1, 3, I have a point. At 4, 4, I have a point. 4. At 9, 5, I have a point. So that's 4, 5, 6, 7, 8, 9. Roughly there. And so you can see my curvature just like so. So, ladies and gents, that is all that I have for section 10.1. It's a lot of information introducing you to radicals, so I highly suggest going back through, getting a lot of practice on this section. All right, I have another lecture coming up in just a moment.